ladies and gentlemen, we call this slow recovery. If I run this right now, I haven't changed anything, so it's not going to be a slow recovery. What would I have to do to make this a slow recovery? Can anyone say I actually gave you the hints earlier? First of all, who is it that worries about recovery? Is it something in Maine or is it something in person? It's something in person. It's an aspect of personhood, how quickly they recover. It's an aspect of personness, and that's described by the person class. Person class is responsible for creating lots of particular people, but they all hew to this notion of personhood. They all sort of are just different minor variations around this notion of a person. They're all people with individual characteristics. Okay, so where here would we look for recovery? Well, recovery, as I said earlier, it occurs down in this place here. And in fact, we saw when we selected this before that there was a rule for how quickly that recovery occurred. And it said it occurred with a certain rate, a certain hazard, I noted, which is given by 1 over the average illness duration. Whoa. Sorry, this thing was encoding a video at the same time. Okay, so it's 1 over the average illness duration. And you'll notice it refers to get Maine here. In other words, this is something that lives in the Maine class. It's associated with Maine. So we actually have to look at Maine to find this average illness duration. And we'll find it here. It's a parameter of Maine. Now, what it means for it to be a parameter of Maine is we can specify it very easily in this experiment. If you have something in this model that has a parameter, it means whatever it creates that thing can easily specify an alternative value for that parameter. So in this case, if we go to slow recovery, we'll find that there's a set of parameters we can specify. The default illness duration is 15. Ladies and gentlemen, let me present to you a proposal to make that 50 instead. 50. We go from 15, 1-5, for the average illness duration to 50. Okay? So let's go down to that and change this to 50. Okay? So, ladies and gentlemen, we saw the model run at sort of baseline configuration. It's configuration with no alternative changes, sort of the default values for parameters. And we saw its behavior as a whole. The behavior of the whole was different than the behavior of the sum of the parts. No one individual exhibited this kind of growing circle, but the population as a whole did. And that's all well and good. But how does changing this parameter so that people have a slow recovery, how would that affect things? How would that affect what we saw? Anyone? Okay, so you're ill for a longer time, that's true. How will it affect the overall behavior? Like, how would that affect what we saw?
More red.
Okay, there's going to be more red. Okay, great. So big red. Is that red going to occur scattered throughout everywhere? Is it going to occur in the heart?
Focused at that front, at the wavefront.
Okay, it's at the wavefront. The red, the greater thickness is going to occur at the wavefront. It's going to occur in that frontier, as it were and this is an analogy that actually carries a great deal of conceptual substance to it. It's like the prairie fire of a burning thing, all that front where it's going along. And so in this case, I'd like you to go up and run it. How did I run it again? Let's show that for those who are new to it. I go and I right-click here and do run, or I can use this one up here again. This is going to come up here, and let's see, there we go. And let's run this. So we're going to get thicker wavefront. So let me ask this, folks. Now people are going to be thicker for longer. So they're sicker for longer. They're ill longer. They're infectious for longer. It sort of stands to reason that you would think that they are going to infect more people. So there's going to be more people infected, and maybe that's going to speed up how quickly the infection propagates. So how many people here think that this is going to speed up how quickly the infection propagates out? People are infected longer. Is that going to mean it travels faster? Or why not?
Because the contact rate is constant. It's just the number of people, susceptibles they come in contact, we have not changed that.
That's true. So that means per time infected more people, but they're infected for a longer period.
They are infectious, but the contact with the susceptibles is limited.
Okay, it is limited, but they are infectious longer. Does that mean they infect a greater number of people over the course of their illness? Of infecting someone?
It would until some sort of maximum value.
Until there's some sort of saturation. A saturation regime.
They've infected everyone they know.
That's right. Look, you can only infect people around you once, right? Like, all the people around you, there's people sitting north, south, east, and west of you. You can only, what's the maximum number of people you can infect?
Three. One infected you.
One infected you? Okay, nice. Yeah, good call. Okay, so 3 extra people you can infect. The fact that they're infectious longer, is that going to lead them to infect a greater number of people then?
Up until 4.
No, just 2, yeah, so it could be. So in this case, there are stochastics. You'll notice that there's chance operating here. Who happens to get infected first? And it's possible that we could, in this case, it actually is possible that all of our in this airborne illness is going to one person. That person's infected. We never infect them further, or it keeps on going to the person who infected us, infect anyone else. That isn't theoretical. But in this case, it's a very marginal effect. You'll also notice, for a variety of reasons, the model is running slower, and we'll talk about that later in the class, why that is. Fundamentally, there's more events being handled, so it actually needs to do more work to advance it. But you'll notice that there is indeed this thicker boundary, around the number of people recovered. And you'll notice that this inner area of gray, it takes actually a much longer time until an area of gray becomes free of infectives. Why? Why are there so many more reds in here? Because
Average illness time.
yeah, they're staying infected for a much longer time. So it's not merely these folks out here. These folks down here are still infectious. They're still coughing and sneezing and wheezing and potentially infecting someone, but there's no one else to be infected here. So really they're not having any action. Where's the action? The action's occurring at the edge of this prairie fire. This fire which is spreading around the periphery. Ladies and gentlemen, if we ran this out and we were to time it with model timer, we would find it reaches the boundary virtually no faster than the other model. Now this is no faster than for that other case with the shorter illness. Now this is significant because it turns out many models will be using, many aggregate models which don't differentiate individuals. Having someone infected for longer is going to mean the infection is going to travel faster. It's going to spread faster. And so this model actually captures the fact that, no, that's not the case. It's a saturation phenomenon. It can only infect so many people. And if you're infecting that many people with the average illness duration being 15, increasing it to 50 is not going to matter much. Okay, so we've seen there, some change. We might think, numerically, we increased how long people are infected by more than 3 times, right? Wouldn't you think that would, worsen things? Well, it doesn't worsen in terms of how fast it spreads or the total number that get infected, because after all, before everyone was getting infected. It actually has a pretty marginal difference. In nonlinear systems, you see this a lot. Some parameters, it's very insensitive, and some, ladies and gentlemen, it's going to be very, very sensitive. We may push it to a tipping point where a small difference makes a huge difference. I don't know. Okay, so we ran this, and if we had run it long enough, we would have seen something like that, although the center of this depends on the vagaries of who selected initially, and we can go see where that's done. Okay, so ladies and gentlemen, thus far we have modified we have modified some aspects of the model, not really modifying the broad outlines of the theory. We haven't changed sort of our theory of sort of how people's illness progresses here. We've changed some of the detailed assumptions. For how long we're assuming someone stays affected. We've changed that, but we haven't really changed in a substantive way our theorizing. And now we will do so. Okay? So what I'd like you to do is I'd like you in your first little exercise here in changing a model and modifying a model, I'd like to add in a situation which depicts a situation where an individual doesn't stay recovered for life. In other words, someone who's been infected, they lose their immunity after a certain amount of time. Mm-hmm. So thus far, we've had a model where once they're recovered, they stay recovered. True or not? True. We're going to want a situation where they can lose their immunity after a certain period of time. How are we going to do that?
Put an arrow that goes to the other.
Good. We put a transition, we'll call it, which goes from where to where? To susceptible. Okay, so we're going to do that. So, ladies and gentlemen, I'd like you to, we're going to, again, this is going to be a recurrent issue with these models. What are we describing? This is the theory about what? Is it a theory about Maine? About how Maine works? About how the environment is changing for all people? No, it's a theory. We're changing the theory about how what works. Person. So we have to go to person. Person is where you know our changes are going to focus. So we go to person, and now we're going to go over to the palette. And ladies and gentlemen, it's out of the palette that you will paint your masterpieces in this class. So I hope. Okay, so within this palette, you'll have a bunch of different choices here, and we'll come to a number of them later. The one I want you to focus on here is, went down a little bit too far, it's this one called state chart. Okay? There's this transition here, and I'd like you to drag out this transition. And you'll notice out comes the transition. And you'll hitch it up, drag it over so that it's coming from recovered. And you'll notice that when it docks properly, it will turn green. Okay? If that didn't work, if you dropped it prematurely or it didn't hitch up properly, you may see it actually remain white on its end, and you want to drag it over. Okay, so let me see if I can get it to. No, I'm not able to get it to do that. Okay, yeah, it would look like this, and you can drag it over there onto the state here. And what will happen then is it should the end of it should turn green here. I don't know if it's the encoding or what, but my computer is just totally maxed out, so it's going extra slow. So then I'd like you to take the other end of this, and I'd like you to drag it up to susceptible, putting aside concerns of aesthetics at the moment, putting aside concerns of prettifying it. We'll prettify it in just a little bit. So drag this other end up to susceptible. Okay. And once again, it should turn green up on that end. Okay. Let me just because this is getting brutally slow. Pardon me for just a second. Yeah, I think it's just a result of the different things I'm running to do this class. Okay, nothing odd there. Okay, so having done that, what I would like you to do is to prettify it by going and double clicking here partway through it, say over here, you could double click, and that should put a little divot in it, a little handle, and you should be able to drag this handle off to the side to route it out of the way of those other states. Okay. you folks whose computers will be less loaded than mine might want to put 2 divots. I will limit myself to 1 here. Okay? So now we have a situation where we've extended sort of the broad outlines of the theory. We've sort of mapped out what we want to do. Is this model ready to run? Is this model fully articulating a theory yet?
Probably not.
Okay, what do we need to do to sort of more completely specify this theory?
We need to define what that arrow does.
Yeah, like we need to give it some semantics. Like, okay, this is great. So basically this arrow is telling us someone can go from recovered to susceptible. That's great. And that sort of model map is useful for talking at a high level about this. If you brought this, we in our work, we bring these things all the time to physicians or whatever, we show them, and they understand what this means, and that's great. But really to make it precise, to make it quantifiable, to make it more rigorous, we're going to want to be precise about what the semantics of that arrow, what that arrow mean. Under what conditions will they make that transition? Will they make that transition under conditions of, someone contacts them, a doctor does something to them? Do they make that transition under a situation where they reach a certain age? Do they do that just at a certain rate? We're going to have to dictate those things. We're going to have to encode the logic, the rule behind underlying that transition. The semantics, the meaning of it. Okay, so ladies and gentlemen, this transition, I'd like you to name it, just having selected it, I'd like you to name it waning immunity in so-called camel case there. You could see it spelled out. And that camel case, of course, is used to indicate the division between different words when we don't have the luxury of putting spaces in between. Okay, so waning immunity is going to be the name of this transition, and I'd actually like to show the name so it's more transparent with this little box here. Okay, and then, ladies and gentlemen, we're going to lend it more precise semantics. So you notice it says waning immunity here, and you can actually drag this up and reposition it elsewhere here. But in the meantime, I want to also associate this with a timeout of time 100. Now, a timeout is different. Ladies and gentlemen, earlier we saw semantics associated with recovery transition. And I made a point of emphasizing that recovery had a meaning to it. There's a certain logic to it. What was that logic? Under what situations would recovery occur? Did that depend on a doctor administrating you antivirals? What was this dependent on? What was this recovery dependent on? Sorry?
The average illness.
Okay, and in what way was it dependent on average illness duration?
1 over.
Okay. It actually had, was it an exact time of average illness duration? No, it was a rate. And it was a chance per unit time. Each little bit of time you had a kick at the can. You have a certain chance per unit time, and exponentially distributed distribution associated with how long you remain here. We're going to get to that later in this course, what that really means. But you have a certain chance per unit time. No matter how long you've been there, a certain chance of leaving. If you're still there, you have a certain chance of leaving the next day. Here, we're going to do something quite different. Here, ladies and gentlemen, we're going to associate with a precise amount of time. Exactly after 100 days of having been recovered, you're going to lose immunity and return to susceptible. Okay? This is going to lend itself to a different sort of behavior. Okay. So we're going to do a timeout, and the timeout is going to be 100. Okay. So, ladies and gentlemen, how will that theory change things? You've seen how the earlier theory, the theory where we had susceptible, infected, recovered in a sort of sequence, we saw the behavior associated with that, and there's some pretty good explanations proffered from those in the class here. Explanations associated with spread to neighbors, with saturation effects. And that's great. Excellent. How will adding this transition change things?
Have a ripple effect.
Okay. So I hear some good terms, and I think I know what's meant by them. But sorry? It may never be stable. Before it was going towards a stable equilibrium, a situation where it was all recovered, and we could have sprinkled in, every few time units, we could have sprinkled in new infectives, and they would have just petered out, right? Disappeared. And here there's a comment, it's not going to be stable. Why not?
If the infectious people could reinfect the people who infected them and get reinfected by those people.
Good. So people are going to get recovered after that first wave, but then they'll lose their immunity and they'll end up susceptible again, and sprinkling those infectives in could infect them, right? So it ain't going to be stable there. What characteristics visually, spatially, what would we expect to see different? Are we going to see this big mass spreading out again?
Yeah.
Okay. Are we going to see something different eventually? Okay, so we're going to have gray, and then we're going to have okay, and why will we see red dots in the recovered area again?
Because they become susceptibles.
They'll become susceptibles, and once they're susceptible, they will.
They have chance of getting infected.
Okay, they'll have a chance of getting infected. Will they always become red?
Yellow first.
Okay, yellow first, and then they'll have a kick the can becoming red, right? Okay, so ladies and gentlemen, let's. This is some great commentary. Let's run it. Ladies and gentlemen, let us compute. So let's right-click on simulation. You'll notice I've made a change to the model. Now wait a minute. This is important conceptually. I made a change to the model, and I had these scenarios here before. If I were to run those scenarios, those two scenarios, one called simulation, one called slow recovery. If I were to run them, is it running with the original theory or this updated theory? It's running with the updated theory. For better or for worse. There's no way right now to kind of have multiple scenarios with different model structures, each associated with them, other than make a copy of person. You could have person one and person theory one, person theory two, and have each of those used separately by different mains. It would get very complex. Here, these scenarios still exist. They still specify the parameters in the same way that we defined them earlier, but now they're operating with respect to the updated theory. If we want to keep away around that old theory, one way we could do it would be to create a separate version of the model, for example. Okay, so we're going to right-click. I right-clicked on the normal theory, and we're going to run this now, okay? And I want to run it. And we're going to let the chickens come home to roost. Okay. So we'll see these predictions. Okay, so the model starts. Unfortunately, the suspense is going to be limited to me. And because I think most of you have computers that are not running Collaborate and doing audio encoding twice and trying to record the screen and those sort of things. But what's merely a speck in the cosmic eye on my screen is no doubt reaching full fruition on yours. Okay, so starting, do we see anything different? No. Okay, do we see anything different on my screen? No. Okay. Are we going to see something different?
Yes.
Okay. And how long?
100 steps.
Okay. 100 steps after the first person recovered. We should see something different. And here it is emerging in the fullness of time. So let me go model time up. Okay, the time approaching. Here we are running along. We still see nothing different. One could be excused for thinking that we haven't changed anything about the model. Maybe we're running the original model theory, as it were. Where should I look for a difference? Out here? No. In there. Ah. Okay. The seeds of doom. Okay, so we see here in the center the emergence of what? Okay, susceptibles. Now, those susceptibles, are they getting recovered? Are they getting affected? Okay, now they are. They're just starting to get infected. And if we run this out, what will we see?
Unstable, perpetual disease.
Okay. And what would, if we were to draw out over time the number of people infected, total number of people infected at a given time, what would we see? Just crudely speaking. In the original model, what did if we drew out here on the board the number of people in the original model, so before the original theory, before waning immunity, what would it have done?
Roughly the correct one.
Okay, so number infected, it would have gone. You might have thought it would increase. It will actually go fairly linearly here, and then it will go something like this as people recover. Something on the order of that. What will this do? Okay, so there'll be an oscillation of some sort. There'll be an oscillation over time. We'll see how we can do this in future sessions. Actually add, you'll notice here you add bar charts, pie charts, time plots of this, which would allow us to dive. So what's happening here, folks?
There's a second wavefront.
Okay, so there's a second wavefront. And here are some susceptibles inside of that may have persisted, or maybe a third generation of susceptibles coming. Okay, so where are these waves in the model? Are they here? Is this a wave? Where are waves?
They're implicit.
They're implicit. This is implied somehow in some complex way, in a way that may not be totally obvious. This whole structure and the islands of red you see, and sort of this mixture of regularity and stochastics, these sort of regular structures, the orderliness, but at the same time some of the stochastics. This is all implicit in that small, crisp definition we've given, but it's suggestive of considerable complexity. And now, ladies and gentlemen, I will ask, how would this be different yet if we were to run the slow recovery? Let's run the slow recovery here. How would that be different? Well, you'll see something like this. Why is that?
As soon as you become susceptible, everyone else is still infected, so you're instantly reinfected.
So you're instantly reinfected. So now you get a situation where there's some scattering of recovereds in here, right? But those recovereds will eventually become susceptible and infected, and then they'll recover, and then they'll become. So it'll be kind of this mosaic, this patchwork of infectives and recovereds, all sort of propagating out here, and it'll become this miasma, this magma of sort of recovery and new infection here. Okay, so well, yes. So I asked about timing and so on. So we'll get to this issue of a random mixing model and so on. So a couple take-home points, because soon it is time to take this home. Within AnyLogic, we've seen a brief glimpse of AnyLogic and AnyLogic's environment here. AnyLogic is a declarative, largely, in many ways, it has many declarative elements to it for specified models. We've seen that models are associated with graphical representation that has real semantics associated with it. It's not merely a sloppy diagram showing things. It has meaning to it. Those things we saw on the screen are called what in computer science or UML? They're called state charts, yeah, and they include states. We see them in UML to describe software systems. Here, they're being used to describe a certain type of software system, to describe semantics associated with agents within an agent-based model. That's a program, and we're using it to specify elements of that program. Everyone here who had their hands on the keyboard and was changing things has now done some Java programming. Those were actually little snippets of Java we were typing, and we were when we set, for example, the time to waning immunity of 100, we could have put in an arbitrary Java expression that read Saskatoon's weather off the internet and use that to determine the time to lose immunity. So if it's really cold out, you lose immunity faster or something like that. Running a structurally simple model, a model with a very, very simple theory, very simplistic theory, can lead to very complex emergent patterns over time and space. These are patterns over time, sort of oscillations, and I challenge some of you, maybe try to do graphs of some oscillations. Maybe I'll send out a little exercise about that. And yet we also saw emergent patterns over space. Again, generated by this very simple description, very, very simple, concise description leads to these very complex patterns over time. Modifying the model quantitative assumptions, described by parameters in this case, so characterize our assumptions. They communicate those assumptions from the creator of something, like the creator of main to main itself. And modifying model structure can qualitatively change the model theory and therefore model behavior, sort of whole modes of model behavior. Changing parameters can also change model behavior in some notable ways. Consider the difference between the situation where we had this versus the situation where we had this. We see rather different behavior just due to differences in parameters. That difference associated with how long people remain infected. But even more fundamental than that, ladies and gentlemen, is what happens when we change a model structure. Change how things work in that model. Change sort of the theory associated with it in a deeper way, going back to something, for example, with waning immunity. So these are some take-home points about this. Any logic is going to accompany us through most of this course. It supports all three sorts of modeling we're going to be examining: system dynamics modeling, agent-based modeling, and discrete event modeling. And in fact, allows you to weave them together in very flexible fashions. So you can have a single model with multiple types. Okay. Next time, we're going to be going on, and we're going to actually be using VenSim some for probably for the next couple lectures, because it's a particularly useful vehicle for, among other things, drawing some diagrams out in a more model mapping sort of way, and for doing some quick experiments with system dynamics modeling. So those are all my comments for today. I have released a number of possible project descriptions, and I'm expecting one or two more to come in over the weekend. So I would suggest if those interested in projects, you're welcome to go online and find those projects in the Moodle site for the course. I did also want to emphasize to people that if people have ideas for projects where it would be a meaningful project to outlast this semester, be something that someone would be interested in beyond the confines of the semester, I'm perfectly glad to talk about those projects involving other ideas. But those ones are things that there's actually stakeholders known to me who are very interested in having these projects done, and where successful delivery of the projects could open some interesting opportunities for you as students. Some of those projects have turned in past sessions into papers, into job opportunities, etc. So you might want to look at them if you're interested in projects, just to see if there's something there that you might find interesting. Okay? Okay, so that's all for today. Now I do think I may send out something asking you to probe this model a little bit more is a little challenge. Okay? That's all. Thank you very much.
What do we do at 30